Hello again, and in this lecture we're going to start a new chapter and we're going to learn about the center of gravity and the center of area. And we will do so for a two-dimensional body. So the center of gravity for a two-dimensional body can be established by considering a flat horizontal plate, like in the diagram below. So I'm going to represent the three-dimensional space, the x, y, and z axes. However, our plate is flat and horizontal and lies in the xy plane, in the horizontal x, and this is the y-axis plane. Now, the weight of the plate, the gravity force for the plate, will act at the center of gravity. And the location of the center of gravity is, say, at capital X bar and capital Y bar. And these coordinates are the ones that we need to determine in order to know the location of the gravity force. So we can do so by dividing the horizontal plate into an infinite number of little areas, little elements actually, each of them having a very, very infinitesimally weight. And we need to do so by covering the entire domain, the entire area of the plate. So for example, this would be, say, element number 1, having a weight, very small weight, dw1, located at coordinates small x1 bar and small y1 bar. And then, for example, this would be a next element, element number 2, having a weight equal to dw2 and being located at coordinates small x2 bar and small y2 bar. Now, the original system must be equivalent to the first system plus the second system plus many other systems until the whole area of the plate, the whole plate is covered. For equivalency, as you know, we have to write the two equations. Sum of the forces on the first system must equal to the sum of the force on the second system. So that will give us the weight force equals to integral over the area of dw. And if you haven't studied integrals yet in your calculus course, you should regard these integrals for now as summations. And also for equivalency, the sum of the moments about a point, let's say O, about the two axes on the first system must be equal to the same for the other systems. So that results again in these two expressions. So capital X bar times W equals to integral over the area of small xi bar dw, and capital Y bar W equals to integral over the area of small yi bar dw, equations 2 and 3. If you look carefully at these equations, equation 1 calculates the weight of the plate really, but equations 2 and 3 can be used for determining capital X bar and capital Y bar, which are the coordinates of the center of gravity of the plate, of the flat horizontal plate. So this is very important to know these coordinates because this is again the location where the weight force acts for this flat horizontal plate. It's very important, so we know where to exactly locate the gravity force. Now, we can look at a particular situation in which we consider, rather than a general plate, we can consider a flat wire, also in the XY plane. So it's similar to the case before, except that we have replaced the plate with a wire. And again, let's look at the wire in the three-dimensional space, but the wire is flat. It lies again in the XY plane. And the weight force would act at a point like G, and would have coordinates capital X and capital Y. And you can see the situation is somewhat similar to the one described previously for the plate. And we can apply the same theory by affirming that the original system is equivalent to a series of systems in which the wire is divided into very, very small, infinitesimally small elements, each of these elements having a weight equal to dwi for element I, and each of these elements being located at small xi bar and small yi bar coordinates. As you can see in these diagrams that I've been doing here, and of course, as I said, the first system has to be equivalent with an infinite number of series of the other systems summed up together. And then we can write similar equations for equivalency. And then what we will obtain is, firstly, W equals to integral over the length of the wire of dW. That would be equation number 1. And capital XW equals to integral over the length of the wire of small xi bar dW, equation number 2. And finally, capital Y bar W equals to integral over the length of the wire of small yi bar dW, equation number 3. So equations 2 and 3 will again help us determine the coordinates of the center of gravity of the wire, whereas the first equation will give us the weight of the wire. Same as before for plate. Similar equations, similar principle. However, there is one major difference, and that is that in the case of the wire, depending on the shape of the wire, the center of gravity for wires is generally off the wire. It's not located directly on the wire. It's usually somewhere in the air, off the wire, as I said. So these are the ways for determining the center of gravity for plates and wires. Now let's talk about another concept, and that is the concept of a centroid of areas and lines. And let's begin with area, or areas firstly. And if we consider an area that is of a flat, homogeneous plate of uniform thickness, so these are the three important characteristics: flat, homogeneous, and uniform thickness, then we can express the weight of the plate is equal to the mass times the acceleration of gravity, and the mass will be equal to the density times the volume, and hence the weight in the end will be equal to the density times the area of the plate times the thickness of the plate times the acceleration of gravity. So again, rho is the density of the material the plate is made of, A is the area of the plate, and T is the thickness of the plate, the uniform thickness of the plate. If we now substitute the expression of the weight of W, rho times A times T times G, into the equations 2 and 3 that we derived for plates, then we will end up with the following expressions. Capital X A equals to integral over the area of xi bar dA, equation number 4, and capital Y bar A equals to integral over the area of yi bar dA, and this would represent equation number 5. These are two very important equations because it will help us determine x bar and y bar, which are the coordinates of the centroid of the area, which coincides with the center of gravity of the plate if the conditions mentioned above are satisfied. So the plate is flat, homogeneous, and has uniform thickness. So for such a plate, all we have to do is determine the centroid, and the centroid will be also the center of gravity, and that's the point where the weight acts. Now for wires, again, if we consider a flat homogeneous wire of constant cross section, then the weight of the wire can be expressed as rho, the density of the wire, times L, the length of the wire, times small a, which is the cross-sectional area of the wire, which is constant along the wire, times g, which is the acceleration of gravity. Then we can derive similar formulae. And that will be x bar times L equals to integral over the length of the line times xi bar dl, equation number 6, and y bar L equals to integral over L of yi bar dl, equation number 7. And these two equations are also very important because they help us determine the coordinates of the centroid of the line or wire. So again, two sets of very important equations. Now they're expressed in integrals, but you will see that we don't have to use integrals in our problems, and that would be easily shown in the next lecture when we will actually study the centroids of composite plates and wires. Thank you very much for watching this lecture, and I will see you at the next one.